was a nice get together. We are looking at limits at infinity. We will, once I get this camera going. There we go. And we're going to, in particular, find out how to find the limit as x tends to infinity or the limit as tends to negative infinity. Right, so that's what we're focusing on today. There are 4 techniques. I'm not sure whether we'll get through all 4 today, but we'll certainly get through a few of them. And one is numerical, where you basically get an estimate, and you do that by a table of values. And the second method's really quick. It's called brute force. Connected to the brute force method, there's another method where you divide the top and bottom by n squared, n cubed, things like that. I'll show you those. And then the last one is probably the least used, but there are a couple of questions where you use a thing called the sandwich theorem. So let me start with numerical method. Let's suppose I wanted to know the limit as x tends to infinity, right, of x squared over e to the x. One way to do that would be to just do a table of values. So you do x, and then you evaluate x squared over e to the x. And you do as many numbers as you like, but I might start at 1 and then do 10, then do 100, then do 1,000, and then maybe 10,000, and then maybe finish with 100,000. If these numbers, as this gets bigger, if these numbers are homing in on a number like 0, then that would be the limit. If they're getting bigger and bigger and bigger and bigger and bigger, won't the answer just be plus infinity? If they go, 0.4, 0.49, 0.4998, can you see that the limit there would be a half, right? So you basically you look for a pattern going in this direction, and then you can make a conclusion about what the limit would be. Of course, if the numbers just jump all over the place, then you would say that the limit doesn't exist. So I'm going to do the table trick. So I hit y equals 0, and I'm going to put x squared divided by e to the power of x. And then I'm going to go second table setup. And just make sure that that guy that says ask is highlighted. That's all you need to do. So second window, table setup, make sure that says ask. And then second table. And I don't like these answers. They're from other questions. So you type in 1, 10, 100, 1,000. Oh, okay, that will do. I wasn't expecting the error, but I think I know what happened here. So it's about 0.367, then it's 0.0045. Now, see the next one, it looks weird because it is. It's 4e to the negative 40. That is the TI-84's version of scientific notation. In other words, 0.39 other zeros in a 4. Would you agree that that number there is essentially 0? Now, you might say, what did that error come up with? I think what happened here is that the poor calculator just keeled over and died, because e to the power of 1,000 is just too hard for it, right? So that would be that one. So in this case here, I would assume that the answer is 0. Let's suppose I wanted to find the limit as x tends to infinity of x squared plus x over 2x squared, take away 1, right? In the same way that I just did here, if I'm doing it numerically, I'd press y equals. I'd put brackets around it, so it's going to be x squared add x on the top, close the brackets, divided by another set of brackets for the bottom, 2x squared, take away 1, close the brackets. And I've already done the table setup, so once you've done it once, ignore that step. Go to second table, hit delete to get rid of the old stuff, and here goes. You put in 1, you get that answer. You put in 10, you get that answer. You put in 100, you get that answer. You put in 1,000, you get that answer. Maybe one more, 10,000. What do you think the limit is based on the pattern that you can see in this table? Look at these numbers. What are they getting close? Agreed. Would that make sense? So we would estimate that the limit of this fraction as x tends to infinity is 0.5. If you put it into your calculator, I bet you at y equals 0.5, I bet you've got one of those functions that, you know, the horizontal asymptote thing happens. That's essentially what you're finding. Are we good? Do you need to see another one of these? Or are you pretty comfortable with these? You tell me. Okay, I see pictures, but I don't see any or okay. You can do that if you like. Okay, since I don't see that, I'm assuming that maybe you want one more. So let me pick one, and it's this one. The limit as x tends to infinity of x cubed over 3 to the power of x. And I'm going to do 10, 100, 1,000, maybe 10,000, right? You really stop when you think you're happy with your conclusion. So I'll go to my calculator again. I'll hit y equals, rub out the other one by hitting clear, put in x cubed, that's x to the power of 3. I'll divide it by 3 to the power of x. And then I'll go to second table. And if you put in 10, the answer is about 0.016. Put in 100. Oh, we've seen that weird thing before. What does 2e to the negative 42 look like? Isn't it an awful lot of zeros? I don't think I need any more. Would you agree 0 is my conclusion? This number was 0.016. This number was 0.00, another 39 zeros and a 4. Oh, a 2. No, that matters. Would you agree that's darn close to 0? So 0 is my answer. And that is the numerical technique. Now, if you were lazy, couldn't you just pick one value for x, but pick a really big one, like 1,000 or maybe 1,000,000? And wouldn't that pretty much give you what you're looking for? Provided it's not this case. And this is why you need to check. I won't do the table part, but here we go. I'm going to put sign of x in, and let's do a table. There's 10, there's 100, there's 1,000, there's 10,000, and there's 100,000. That's interesting. That's very interesting. That's not what I expected. That is very weird. Doesn't the sine function bounce up and down between 1 and -1 quite randomly? I was expecting to see a whole load of random digits. Let's clear that out for a minute.
You just happen to get all of the ones as it bounced to the same spot?
Yeah, pretty much, and I didn't expect that. So I'm going to be random about it. 22, 22, 90, 105, 198, 256. Ah, can you see the randomness now? Right. I guess the moral of that story is maybe don't be so nice about your X's, right? Make them bigger, but kind of, mix and match them a little bit, because that was a freak. Wasn't that a weird one? That I just happened to be snapshot in the same spot. Wasn't expecting that. So in this case, you would say that the limit as n tends to infinity does not exist. If you got a table and it looked like this, right? So we did it at 10, 100, 1,000, and say 10,000. Let's suppose we got a table and it's 5, 27, 319, and 42,011. Wouldn't that be an indication that this has a limit? But won't the limit be infinite? Right, you agree? As you travel upwards, doesn't the answer just get bigger and bigger and bigger? But I feel a little bit more comfortable now. Are we good to move on to brute force method? Right. So, let me tell you something that we pretty much assume is obvious. In the brute force method, you essentially replace the x with infinity, and you try and find out what the answer is. So let me tell you what is allowed. 1 over x gets you 1 over infinity. 1 divided by infinity as a limit process is in fact a number. What number do you get if you take 1 and divide it by infinity?
0.
You get 0. And we assume that is pretty obvious. Now, if you take the limit as x tends to infinity of 1 over, well, let's put it as 10 over x to the 4, you get 10 over infinity to the power of 4. Isn't infinity to the power of 4 still infinite? You mean, yeah, it's a different kind of math. Would you agree that infinity times infinity times infinity times infinity is just an infinity, right? It's still infinite. What does 10 over infinity get you?
Still 0.
Still 0. There's a theme here, isn't there? What does 11 divided by the square root of infinity get you?
Still 0.
Right? In fact, isn't the square root of infinity still infinite? It's still infinitely big. We are going to use these guys to help us understand other limits. So if someone went and said to you, I would like to know the limit as x tends to infinity of 4 over x cubed plus 1. Brute force would say 4 over infinity cubed plus 1. And then you do some weird math. Would you agree that infinity cubed plus 1 is still infinitely big? You agree? Infinity cubed adds 1. And isn't 4 over infinity 0? Do not be surprised if a lot of these answers could be 0, right? Now, make it a little bit trickier. A weird calculation, but just imagine that somehow or other this weird calculation happened, right? According to brute force, we should be able to do this guy. Okay. Would you agree 2 over infinity is 0? So the top is 1 plus 0. What would negative or take away 2 over infinity squared? What would that get me?
Infinity.
2 on the top divided by infinity squared.
Yeah,
just
0.
that. Just get a 0. And so wouldn't the answer here be a third? Just to show you, you don't always get 0 when you do brute force, right? There are situations. Here's one. Ooh, be careful. If you wanted to work with this question, I strongly suggest that you rewrite it like that before you do the brute force part. So now it's 3 on the top and e to the power of infinity on the bottom. Would you agree e to the power of infinity is just infinite? And so according to our rules, won't the answer be a 0? Let's do another exponential one. Now I can't really do anything with that except plug in infinity. So e to the 1 over x becomes e to the power of 1 over infinity. Now we've done 1 over infinities a lot, isn't that 0? But be careful. E to the 0 is in fact a number, isn't it? 1. So that one would be equal to 1. Any questions about these brute force? I mean, there's lots of other versions that you could do. Are we good with it so far? Let's do a trig one. Let's see what that guy looks like. So it's going to be the sine of 1 over infinity plus 2 times the cosine of 1 over infinity squared. 1 over infinity is 0. So that becomes the sine of 0. 1 over infinity squared is also 0. The sine of 0 is 0, but the cosine of 0 is 1. So in fact, the correct answer to this one would be 2, right? So brute force basically says when it's doable, right? Because sometimes it doesn't work. You essentially just plug in an infinity where the x is. And then you do some kind of, I guess I call it infinity calculation, right? A calculation with infinities in it. Normally those pieces, don't they get you zeros? Normally, you'd expect that. Although you could get infinite, I guess, as well. So far, so good. Right now, I've only dealt with plus infinity, so I think I should show you a negative infinity. Well, if you do brute force, you get negative infinity squared. Negative infinity times negative infinity is plus infinity, and the answer is still 0. You see, it doesn't really make a heck of a difference, does it? Isn't 4 over infinity 0 and 4 over negative infinity also 0? Right. Like 4 over negative 10 to 2 trillion, isn't that answer 0, essentially? Doesn't matter if it's plus or minus. So that's one of the reasons I didn't focus on the negatives, because they do pretty much the same answers that you would have got, right, for most situations. And I just thought of one where it wouldn't be the same. So here goes. Here are 2 identical questions, but with different answers. This guy is e to the power of infinity, so won't the answer here be infinite? Right. This guy is going to be e to the power of negative infinity. And the best way to think about what that is equal to is to think of it as 1 over e infinity. which is 1 over infinity, and that's 0. So do you see that there are going to be some circumstances where the limit as x tends to plus infinity might not be the same answer if you did the limit as x tends to negative infinity, right? So it can happen. But most of the time, won't they be the same answer in both cases? Most of the time. Are we good with brute force? Can we move on? Got a nod? That's good. So we're now going to show you one of the major techniques, very, very common technique, the one you're probably going to do most, in fact. And this technique is you divide, or dividing, the numerator and the denominator method. And let's show you why we even need this method. Let's suppose I wanted to find the, oh, I've got a 3 there. Let's suppose I wanted to find the limit as x tends to infinity of that ugly fraction function, that rational function. If I tried brute force, it ain't going to work. Let's attempt to do it. Infinity squared, 4 lots of infinity, add 1. 3 infinity squared, take away 3 times infinity, add 1. Right, infinity squared is infinite, 4 infinities is infinite, and 1 added to it. Would you agree that the top ends up being plus infinity? Right, infinity squared, add 4 more infinities, then add a 1. Isn't it just infinitely big? Positive, infinitely big. Now, if you do the bottom, infinity squared times 3 gets you infinity, and negative 3 times infinity gets you negative infinity, and then you have a plus 1. You are not allowed to add infinities or subtract infinities, in particular subtract them. So you might say that guy cancels out that guy, and so the bottom is the number 1, right? You might think that, but that in fact is not true. It isn't equal to 1. And here's a really annoying thing about infinity is that some infinities are bigger than others. And you might think, no, that doesn't make sense. Infinite is infinite, right? You can't have one infinity being bigger than another infinity. So let me try and explain how that can happen. Would you agree that there is an infinite number of whole numbers, right? 1, 2, 3, 4, forever. Would you agree there's an infinite number of whole numbers? Great. Would you also agree that there's an infinite number of fractions? Right, a third, 5 7s, 22 19s, right? We agree that there's an infinite number of fractions. But there are more fractions in the world than whole numbers. And let's try and prove it to you. See if you take the whole number 1 and then the whole number 2. Or let's even stick in 0, right? 0 to 1, right? There's only 2 whole numbers, right? 0 and 1. But isn't there a half, a third, a quarter, a fifth, a sixth? Isn't there an infinite number of fractions between 0 and 1? Oh, wait a minute, isn't there another infinite number of fractions between 1 and 2? Isn't there 1 and a half, 1 and a third, 1 and a quarter? Aren't there many, many more fractions than there are whole numbers? But aren't both of them infinite? So isn't it possible for you to have one version of infinite, how many fractions there are, and it's bigger than another form of infinite, how many whole numbers? That's why you cannot take one infinity and subtract the other, because couldn't this infinity be bigger than that one, or the other way around, right? And so you can't really tell what they're equal to. So this calculation here is impossible. Well, let's assume that everything in the bottom was pluses. Well, everything in the bottom was pluses. Couldn't I get infinity over infinity then, right? That could happen. Right? Imagine everything on the bottom was positive. You are allowed to say infinity plus another infinity is still infinite, right? That makes sense. You can add them together like that. Subtracting's a problem. Now, you might think, I know the answer. The answer is 1, but you're wrong. Couldn't that top infinity be a bigger version of infinity than the bottom? In which case, won't those answers not be the same? So I don't want you to think of infinity like a number, like it's 5, because 5 over 5 is 1. I want you to think of infinity a little bit more vaguer than that. It's a lot of stuff, right? An infinite lot of stuff. And that's an infinite lot of stuff. But couldn't this one be all the fractions and this one all the whole numbers? So one of them could be decidedly bigger and still be infinite, right? And that's why we can't do that. So this expression can't be done using brute force. I could do it using the numerical method, right? Couldn't I do X is 10, 100, 1,000,000 and get an estimate, and that would work. But we're going to use this new technique. So here goes. And what we do here is a little bit weird, but it works. As long as you do the same thing to the top and bottom of a fraction, right? So I can multiply the top and bottom by 2. I can divide the top and bottom by 2, right? In fact, haven't we done that trick to simplify some fractions in other places? I am going to divide the top and bottom by x squared. Divide it by the highest power of x. In this case, isn't the highest power of x, x squared. Now let's see what this turns into when you divide the top and bottom by x squared. Well, if you divide that by x squared, you get 1. If you divide this by x squared, you get 4 over x. And if you divide 1 by x squared, you get 1 over x squared. Are you happy about where those 3 terms came from? Divide by x squared, divide by x squared, divided by x squared. You notice 2 of them are really ugly fractions. Right, let's do the bottom. What would you get if you take 3x squared and divided it by x squared? 3x, yeah. And if you took this 3x and divided by x squared, you'd get 3 over x. And if you take this guy and divide them by x squared, you get 1 over x squared. So what we have done is took the original question, the original limit, and turned it into this new guy. The answer to this guy will be the same as the answer to the original, because we haven't really changed the value of the fraction. We've just changed how it looks. What do you think I'm going to do next? When the limit of this and this as x tends to infinity, what do you think I'm going to do next?
Oh, you're going to make all the x's, you're going to brute force and make them 0.
Yeah. I'm going to, you couldn't have said it better. Aren't I going to replace all the x's using brute force method where you just replace it by infinity? And let's see, would you agree 4 over infinity is 0 and 1 over infinity squared is 0? 3 is still 3. 3 over infinity is 0 and 1 over infinity is 0. And just like magic, we now have a limit. Do you see how we kind of changed the question into a different question that we could answer? But that different question, meaning this, has the same answer as the original, so we solved the problem. Is that not a nice sneaky way around the problem of dealing with infinities, right? Because they're kind of nasty things to deal with. But I haven't broken any of the rules here, right? 4 over infinity is 0, right? We all accept that that's true every single time. And it doesn't matter what version of infinity. You give 4 over any infinity, it's still 0. Are we good? See another one then? Let's do the limit as x tends to, I'm going to do negative infinity, although it makes absolutely no difference to the question I'm about to give you. And this guy is going to be 5x squared take away 2x. And this fella is going to be 3x squared plus an x plus a 1. Okay, what do we divide the top and bottom by? What power of x do I divide the top and bottom by?
X squared.
Great. The rule for that is the biggest power of x that you see. So scan the top and bottom. In this case, both the top and bottom have an x squared, so that's it. But see if one of them has an x cubed and the other one only has an x squared, which is kind of my next question. Pick the biggest, right? X cubed. Let's see what happens here. We have the limit as x tends to negative infinity. That guy gets you 5. This guy gets you negative 2 over x. This one gets you 3. This one gets you 1 over x. And this one gets you 1 over x squared. I should be able to do brute force now. 5, take away 2 over negative infinity. 3 plus 1 over negative infinity plus 1 over negative infinity squared. 2 over infinity is 0. 2 over negative infinity is still 0. If you want to call it negative 0, go ahead, but what's the point? Would you agree negative 0 is still 0, right? 0 kind of destroys the sign or something. So what I've got here is 5 take away nothing on the top, 3 add a nothing on the bottom, and the answer is 5/3.
I have a question.
Good, I like questions. What you got?
Can't you just like cheat and then like take away the rest of the ones that
Ah.
are highest x?
I don't like your word cheat, but I like what you said. Couldn't we be efficient and just take this guy away and look at what that is? Can you see the 5x squared over 3x squared gets you 5/3? Do you see that? That's what I think. That's what you're getting at. Is that correct? And you can look at the answer and you can find the correct answer. What I'm doing here is proving that it's 5/3. I can look at that question and know that it's 5/3, but this is the proof that it is 5/3. So think of this question as being prove that the answer is, rather than just find the answer. And it's good in mathematics that we prove things, because sometimes we see patterns and we think they're right because 99 times out of 100 they work. And then that 1 out of 100 special case, they stop working, right? And so we need a process to do that. So to show you what I believe she was getting at, if we take this question, can you see the 1/3 now that we got? Right. X squared over 3x squared simplifies down and you get 1/3. I have no problems with you knowing what the right answer is, because if I did this and I ended up getting 2/3, wouldn't I say, I've made a mistake somewhere, right? There's something not right. I know what it should be, and it better be that, right? So you still have to do this, but I like the shortcut. I like the efficient way. So let's show you some special problems. And in this case, I have an x cubed and I have an x squared. I'm going to do, and it works both ways, but I am going to choose x squared instead of x cubed. And then I'm going to do this question where I divide the total by x cubed and show you get the exact same answer. Now, if you do her kind of cover-up method, which is actually used a lot, can you see that you have a little bit of problem about what the solution is? You might be able to make a prediction. What do you think this limit's going to be based on what I've covered up?
Looks like infinity.
Yeah, it is. It's going to be infinite, right? And can you see the top's going to beat the bottom? Now, let's do the divide and see how that comes out as working. Well, that guy is 5x. Divide this guy by x squared, you get 2 over x. And divide this guy, you get 1 over x squared. And on the bottom, you divide this guy, you get 4. And divide this guy, you get 3 over x. Are we comfortable with that? And let's put in infinity then. 5 times infinity plus 2 over infinity. Take away 1 over infinity squared. And 4 plus 3 over infinities. 5 times infinity is infinity. Add a 0, take away a 0. 4 plus 0. Everybody in the top is still infinite, and you've got a 4 on the bottom. Would you agree that infinity divided by 4 is still infinite? And that's your answer, infinity, plus infinity, to be precise. Now I'm going to take that exact same question and show you that you can get the same answer, but by dividing the top and bottom by x cubed, by x squared, I should say. And so you're going to look at these two methods, and you might say to yourself, I like it better when you do the x squared. I don't like it when you do the x cubed. Or I like it when you do the x cubed, but I don't like the way it looks when I do an x squared. And so you're going to decide yourself, oops, that's an x cubed, which of those two work for you? Because both of them work, right? They're both going to get you the right answer. So it's going to be the limit as x tends to infinity. Divide that by x cubed. Divide this by x cubed. And divide this by x cubed. You get that. Divide this by x cubed. You get that. And divide this by x cubed. You get that. And now we'll do the brute force. 2 over infinity squared. Take away 1 over infinity cubed. 4 over infinity plus 3 over infinity squared. 5, 0, take away 0. 0 plus 0. 5 on the top, 0 on the bottom. I think this is the first time we've divided by 0. And it does equal something, but it's not a number. What does 5 divided by 0 get you?
Infinity.
And isn't that the same answer we got the other way? So you might like the x squared, you might like the x cubed. I don't mind which. Aren't they both eventually going to get you the same answer? But I can imagine some situations where that is easier to do than this, and then other situations where they switch places. Okay.
So is D and E and diverges and infinity the same?
Oh, guys, a great question, and going to be a horrible answer. Plus and minus infinities work for these questions because that's kind of what they want. Does not exist is loosely sometimes used in infinity situations. But to me personally, I think does not exist is for special cases. If I asked you to find the limit as x tends to infinity of this function, right? Would you agree it doesn't go anywhere? It bounces up and down forever. That's the situations which I leave for does not exist, right? If the answer is plus or minus infinity, I like plus or minus infinity. If the answer is a number, I like numbers. If the answer is it doesn't have an answer, right? It jumps up and down, or it does some weird stuff that nobody can keep track of, right? It's not one value. Then that is a DNE question. So for this section, you only use DNE when you see these. In the others, you're going to say plus, minus infinity, or 2, or whatever it chooses to be. It's not a great answer because you will look and you will see in other textbooks or in videos that they would they would get to here and they just say does not exist. Right? When I take over the world, I will make sure that everybody does my version of that answer, right? But until then, only leave DNEs for things that aren't in infinites or numbers. I got another guy to try. Well, God in Himmel, we've got a few minutes, let's do it. One last situation. It's a good place to finish as well. Let's do a limit as x tends to infinity of that guy. What could I divide the top and bottom by in this question?
X
What-
cubed.
And the other choice I could choose would be,
X to the fourth.
right, I'm going to pick x3 because I think in this case x3 comes out nicer. So it's going to be the limit as x tends to infinity of 4, take away 2 over x squared. This guy gets you 5x, and this guy gets you 1 over x squared. One of them doesn't look right. There we go. Now it looks right. And I should be able to do brute force now. 4, take away 2 over infinity cubed. 5 times infinity, add 1 over infinity squared. 2 over infinity is infinite, so that's just 4 take away 0. 5 lots of infinity are infinity plus 0. And now we've got 4 over infinity. What is 4 over infinity equal to? It is a number. What's 4 over infinity equal to?
0.
Agreed? 4 divided by infinity is 0. So the answer to that is just simply that the limit is 0. If I'd done the x to the 4, you would have got eventually the same answer. So it's not like it's going to give you the wrong answer. Say your last name and bye-bye. And I will hang about for any questions that you may have.
Thank you.
You're welcome. We learned some good, cool stuff today, right? Lots of limity stuff.
I had a question.
Yes,
So infinity divided by a number like 4 is infinity,
correct.
but a number like 4 divided by infinity is 0.
Correct. So you just wanted me to verify what you already were sure about? Is that what the question was? Yeah. In fact, any number divided by infinity, won't the answer be 0? And infinity divided by any number, 22 or whatever, is infinity divided by a number is going to get you infinity. So when you see infinities in a fraction, doesn't the answer end up being 0 or a number? You know, when you do the brute force.
I have a question
And
as
the
well.
number is 0. Yes, Yuriko. Yuriko.
5 divided by 0 is infinity?
Yeah. Now, 0 divided by 5 is 0. And I'm going to try to prove to you that 5 divided by 0 is infinity. So let's pick a number that's really close to 0. How about 0.0001? If you did that in your calculator, you would get 50,000, I believe. Now you'd get 50,000. If you take 5 and you divide it by 1, 2, 3, 4, 5, 6, 7 zeros, would you agree that's almost 0? The answer gets even bigger.
Okay,
So-
I never thought to do that. That's a good idea.
Right, are you comfortable about 5 divided by 0 as a limiting process is infinite?
Yes.